Welcome. We are studying instrument transformers, CTPT. Uh, Previously we have studied ideal instrument transformers, but since this is a course on measurements, so it is important to understand the errors, inaccuracies that we may encounter in a practical instrument transformer. Therefore, we need to understand the equivalent circuit of a practical transformer. Yesterday, in an additional video, we have tried to develop the equivalent circuit very quickly. Okay, so we did it in a rush, uh, and I will refer you if you want a better understanding. Please look at the video lectures on electrical machines 2 offered by Professor T.K. Bhattacharya. It was offered by him in the last semester, so you can look at the recorded videos. Look at week 1. Okay, so this will cover basic magnetic circuits, mutual inductance somewhat, and then you can also look at the course on electrical machines 1 offered by the same professor, which is offered in this semester again in NPTEL. Again, so you can look at his videos on transformer, so have a better understanding. If you haven't studied these things before, so you can look at these things, and you can also get his notes from the NPTEL course web page of these two courses. Okay. Okay. So now okay. Now we know that for an ideal transformer, which can be ideal CT or PT, ideal current transformer or ideal potential transformers, because they are anyway transformers. Okay. So, for ideal transformers, these relationships V1 primary voltage by V2 is equal to N1 by N2, this holds. Similarly, I1 by I2 is equal to N2 by N1, this also holds. But for a practical transformer, for a real life transformer, CT or PT, neither of these equations hold true. And then how do we analyze a practical transformer? The way to analyze a practical transformer is to model it with an equivalent circuit like this. So, this is called the equivalent circuit as referred to primary side. Okay. Equivalent circuit is not unique, you can have many different equivalent circuits, but this is one of them. This you can call the equivalent circuit referred to primary, which is made up of an ideal transformer. So, this is an ideal transformer, this part is an ideal transformer, and before it, so at the primary we have these impedances. Okay, R1, this is this reflects the coil resistance of the primary of a practical transformer. This you can call the leakage reactance X1. This part you can call leakage reactance of the secondary side referred to primary AX2. This thing you call mutual inductance Xm. Okay, so if we take an ideal transformer and put suitable values of these impedances R1, X1, R2, X2, Xm before this primary, then this thing together, then everything together, these impedances and this ideal transformer, they together can model a practical real life transformer. So a real life transformer is not an ideal transformer, it is something more. These extra things are added, these non-idealities are added to this ideal transformer, then it becomes a practical transformer. And we also have seen that for an ideal transformer, if R1 is equal to 0, this leakage reactance equal to 0, this impedance 0, this also 0, the mutual inductance, okay, should be infinite. This is possible only if the permeability of the core of a practical transformer is very high. Then you can short circuit this, you can short circuit this, you can open circuit this. Then all these things are gone, only this ideal transformer remains. So that's how an equivalent circuit of a practical transformer becomes same as the ideal transformer when these things are 0 and this thing is infinite. Okay, and you might have seen a slightly different equivalent circuit in your books or in your college school where you have seen possibly only this part. Okay, so possibly you haven't seen this ideal transformer also added in this equivalent circuit, but that is not actually different, that is same as what I am drawing now, because you can check in that circuit you have this right side has current I2 prime and V2 prime. Okay, so then they call only this part as the equivalent circuit, but then the output from this is I2 prime V2 prime, not I2 V2. But if we put this ideal transformer, then we get I2 and V2 at the right side ports, at the output side. So then this entire thing together behaves exactly like the like a practical transformer. Okay, so you might think that this is different, we have studied something different. No, this is same, but I am doing it this way because I believe this is easier to understand. Okay, so and yeah, one more thing I will mention. Is that so this circuit is actually for an air core transformer. Okay, so the equations that we have developed yesterday and this circuit, this is for an air core transformer which has no iron core, no core loss. We also said that the conductivity of the core is 0, but practical transformers use iron core and therefore they have core loss. Now I will just tell how to model or incorporate that also in this practical in this equivalent circuit. How to incorporate that? Simply put an additional resistance, call it R whatever R0. So if you put this extra resistance, then this circuit can model even core loss. We are not deriving it, we are not proving it. Okay? So you may have the question, why this is so. We are not answering that. I am just telling you that please accept, please believe me at this moment that it is possible that if we put a resistance like this, then even the core loss can be modeled for a practical transformer. Or you think in this way that given a practical transformer, we can always put this structure, this impedance, then this xm R0 before the primary, and then you find out the suitable value of this R1, X1, R2, X2, xm R0, everything somehow, maybe by experiment. Okay? Do a lot of experiment and find out these values. If you find these values appropriately, then this circuit, this entire circuit together will behave exactly like an practical transformer, which has core loss, which has coil resistance, which has leakage reactance, everything. So this is what is called equivalent circuit of a transformer. So I am stating this again and again. Okay. Now let's come to the errors. Okay. So let's consider first a CT. So errors in a CT, current transformer. So what do we or how do we use a current transformer? If I have, say, a line, say a transmission line, like this, which is carrying some current, maybe this line is like this. So it has a load, and this side is the source. Okay. So this is a long transmission line, and I want to measure the current in this circuit, in this long transmission line, call it I. Okay. Call it I1. Okay. Then how do we measure it? So we will take a CT. So now this is our CT. This is the equivalent circuit of a transformer, practical transformer. So this can also be an equivalent circuit for a practical CT. So this thing is our CT. So we will do this. We will open this and connect the CT in series. This is a practical CT. This is connected in series, and the output side will have an ammeter. So here we will connect an ammeter. Okay. Now the ammeter reading gives an indication of this current, right? That's what we know. But let's see, where does the error come from? Okay. Say this CT has a nominal turns ratio of N1 by N2 with nominal or rated or nameplate turn ratio is equal to N1 is to N2, which is equal to A. Okay, N1 by N2 is equal to A. Okay. So if we think that this is an ideal transformer, if we think this to be ideal, then secondary current will be equal to A times primary current, right? Because I1 N1 equal to I2 N2, from that you can show that secondary current or ammeter reading this will be equal to A multiplied by this primary current. So we will think, so if ammeter reading is I2, okay, so ammeter reading will of course be I, if this current is I2, then so ammeter reading is I2, so we will think primary current, okay, that means the estimate of this line current here, okay, so this we will assume to be secondary current or ammeter reading by A, 1 over A multiplied by ammeter reading, which is I2. So we will think, if we believe that this is an ideal transformer, if we by chance think that this is an ideal transformer, then this is how we will calculate the primary current from the ammeter reading or the secondary current by dividing the ammeter reading with a factor A, nominal turns ratio. But is this primary current actually equal to I2 by A? No, it's not. But actual primary current is equal to I1, which is not equal to I2 by A. So this is our estimate and this is the true value. Okay, so and these two are not equal, so that's why we will have an error. Now why these two are not equal? Let's see in this circuit, this equivalent circuit. So this is, if this is I2, then I2 by A, this value is actually this I2 prime which is flowing here. This is I2 by A, and I1 is this current which is flowing here, and this current is not same, because some current can get bypassed through this branch. So if I call this current as I0, this is also called the no load current. Okay, so if this, okay, whatever it is, if there is some current which is getting bypassed through this through this branch which is I0, then I1 and I2 by A, they are not equal. Okay, so then we can write from this circuit. So you see this circuit here, and let me write that true current minus our estimate, this is equal to how much? True current is I1, our estimate is what? I2 by A minus I2 by A, which is this current. This is equal to I1 minus, this is I2 prime, is this, and this is equal to I0. Apply KVL here at this point. Okay, so this current minus this current is this. So this is the error. So this is the error, right? Okay, so therefore we have an error. Now let's define two terminology. Now this equation that I1 is equal to this I2 prime plus I0, this is a phasor equation. Okay, so all these are phasors. So it's possible that maybe say I'm drawing it arbitrarily, that say I0 is here, say this is I0, and say I1 is here, or say I2 prime is here. Okay, so this is I2 prime. Then I1 will be what? The vector sum or the phasor sum. So this will be I1. Okay. So this is I1. Now I1 is of course not equal to I2. This is true value and this is the measured value or estimated, our estimate, and these two are not equal. So we can write from this that the magnitude of I1 is not equal to the magnitude of I2 prime. You can see here that according to this diagram, I1 has a larger magnitude than I2 prime. Okay, and so this is called the okay, I'll tell the name later. And also you see that the angle between I1 and I2 prime, this is not equal to 0, call it theta. Okay, so angle between I1 and I2 prime is not equal to 0. Okay, so this theta, whatever it is called the phase error. This is a new terminology we are defining. So the current that we will see if we connect say a oscilloscope here instead of an ammeter, then we can see the waveform also. Then this current will not be in the same phase as this primary current. There will be a gap between them. Okay, and that gap, the phase gap, is theta. That is what we call the phase error. This magnitude is not same. This you can call the magnitude error. We also call it ratio error. Why? Because then also observe that I1 so I2 prime by I2 this is equal to how much? I2 prime 1 by A. Correct? I2 prime by I2 is 1 by A. But I1 magnitude of this. Okay. But I1 by I2 this is not equal to 1 by A, because I1 is not equal to I2 prime. Okay. So we are estimating this unknown primary current using the rated value of A by multiplying or dividing I2 with this value A. That's how we do it. But this is not the correct factor with which we should divide the secondary current to get the primary current. So this is not the right ratio. So this is not the ratio between primary and secondary. So that's why this fact is called the ratio error. Okay. So we have learned two terms, phase error, ratio error. We have learned one another factor is that these two errors are mainly due to this current I0. Okay. So now we can ask the question, how to minimize or reduce the error, phase error or ratio error. What will be the answer? The answer is straightforward. Answer is to minimize or reduce I0. If I0 is 0, then there will be no error. If say there is no bypass current, then I1 and I2 prime will be same. Okay, I2 prime is our estimate, our measured value, and this is the true current. If this is 0, then there will be no error. So now how to minimize I0? To minimize I0 or reduce I0, we have to increase what? These two impedances. If these impedances are high, then of course this current will be low. So you have to increase Xm and R0. Higher R0 means actually what? Lower core loss. So you have to ensure lower core loss if we want to increase R0. Okay. So to get higher R0, we have to get lower core loss. So we need core material, core to have very good laminations, etc., thin laminations, etc. And higher Xm means, now what is Xm or where does this Xm come from? So Xm comes from actually this mutual inductance. And on what factor this mutual inductance will depend? This will depend on the permeability of the core. If the permeability is higher, then we will have more flux. More flux means with less amount of current we can get more voltage. Okay. So that means less current, more voltage, so impedance is higher. So we will that means we have to get higher permeability material. Then we can get higher impedance, higher inductance. Okay. So we need, so means higher permeability. Also we need this high permeability to sustain for long, for enough, it should not get to saturation easily. Okay. So then also core loss will increase. So we have to use materials which has high permeability and which has low core loss. So lamination should be thin. Okay. So this is how to do it. So easy answer. So you have learned ratio error, phase error, and how to minimize them. Now next question. Why do we bother about phase error? If we want to just measure, say, the RMS value of the this line current, this current, Why do we bother about the whether these two currents I2 and I1 in phase or not? Because we bother only about their magnitude, their RMS value. Then why do you need to bother about the phase? We need to bother about the phase. It is important when we are measuring power or energy. Why? Because suppose as I so say there is a source, there is a load, and we want to measure this power with a wattmeter. So let this be a wattmeter with two coils. This is current coil, this is pressure coil, and so say this pressure coil is measuring this voltage, but this current coil is measuring this current through a CT. So this is a CT. Now if this current which is I1 and this current which is I2, they are not in phase, if there is a phase lag or lead between them, then also this voltage and this I2, their angle between this I2 and this voltage will not be same as the angle between I1 and this voltage. So power and energy measurement will be wrong. Okay. So this is why we bother about phase error. Okay. Now okay, so next thing we will discuss another easy point. I forgot what to say. Yeah. So the next thing we will discuss is turn compensation. Okay, I will just tell you intuitively without going into much mathematics now. So we see that I1 is equal to I0 plus I2 prime. So where I1 is true current, true value, this is true value, and this is measured value. And also from this vector diagram we see that okay, this true value is the vector sum of phasor sum of these two currents. So it seems okay, I1 is somewhat less than greater than the I2 prime. So measured value is somewhat less than the true value. Okay. So although this is phasor, so we cannot say it so easily, but roughly, so what we speaking we can say that true value is greater than the measured value. Now therefore what the manufacturers do, okay, they use a slightly different turns ratio than the nominal turns ratio. If the nominal turns ratio is, if nominal turns ratio is n1 by n2 equal to a, then the CT is manufactured with a slightly different turns ratio, with a slightly different turns ratio. maybe like say N1 by N2 new, okay, where say where I will choose N2 new to be slightly lower, slightly lower than N2. Okay, if I choose this actual, so in or call this actual, N2 not new, actual is slightly less than the nominal, N2 nominal. Okay, then what will happen? The secondary current will be slightly more than the nominal value. Okay, so then the secondary current, so we know this relationship I1 N1 is equal to I2 N2. So if we take this value N2 to be slightly lower, if this value is slightly lower, then this value will be slightly higher. Okay, so therefore we will get slightly higher reading. And the problem we have seen that true value is less than measured value, or true value is greater than measured value, or measured value is less than true value. So with this arrangement we can get that error somehow compensated. Okay, so this is called turn compensation. Okay, so CT will be manufactured with a slightly different turns ratio like this. Okay, now I will discuss a very important point about CT. So you might have heard that a CT should never be kept open circuited. So why? Why should a CT be never open circuited? Okay, why should the secondary of a CT? Okay, so this is very important question. Okay, so no matter whether you understand why or not, if you are an engineer, if you are a practitioner, never ever by mistake open circuit the secondary of a CT. If you have to say replace this ammeter, then before you open this, you put first a shunt resistance or some shunt impedance, then you open this ammeter, put the new ammeter, and then you remove the shunt thing. Okay, so no matter whether you know why or not, if you are a practitioner, if you are an engineer, never open the secondary of a CT. Okay, so if this is the line, this is the transmission line carrying current I1, if this is the secondary of a CT which has this ammeter, if you want to replace the ammeter, first connect a shunt impedance, first connect a shunt impedance, and then replace the ammeter. Okay, this is very important, otherwise it will be very dangerous, it will be very risky. Okay, so no matter with whatever you do, you should never make the secondary of a CT open circuited. Okay. So you first connect this switch, then replace the ammeter, and then disconnect this switch. This is how to operate it. Now the question is why? The answer is as follows. First, observe that a CT is normally a voltage step up transformer. Why? Because it steps down the current. So that means secondary number of turns should be more than the primary. So voltage should be stepped up. Any transformer which steps down a current, it should step up the voltage because of the conservation of volt ampere. Okay. So because CT steps down current. One fact. Okay. So observe this. This is one fact. Next, second thing. So in the equivalent circuit, so this is the equivalent circuit of any transformer, also including the CT. Now here you can put an ideal transformer. I am drawing it symbolically. Now, so this is the equivalent circuit. So this is the main line carrying the current I1, and here we can have the meter or so. Okay. So this impedance you call it Z2. This can be the meter or whatever itself. Now this is an ideal transformer. Therefore, if the turns ratio is A, then the reflected impedance between these 2 points you can compute. We did it assuming ideal transformers. So the impedance that we will see between these 2 points A and B, as seen from this side. Okay. So impedance, or call it equivalent impedance, between AB, this is equal to A square Z2. Okay. Now, so if Z2 is equal to infinite, that means open circuit, then this is called this ZAB. This is also infinite, open circuit. Okay. So this is infinite. So this will imply what? This current, which is I2 prime according to our notation. So I2 prime will be equal to 0. So this side is not there at all. This part is gone. I mean, from here to here, this is not effectively there. And now you observe the point 2 is that this impedance XM and R0, XM and R0 are very high. Why? This is by design. We have manufactured the CT to have Xm and R0 very high. Why? To reduce phase error and the ratio error. Okay? By design to reduce error. This is what we have done. And now this has created another small problem. The problem is that so this impedance is also very high. Okay? So therefore, the total impedance say between these 2 points, call it CD. So let's see it from this way, ZCD. So ZCD is what? This impedance, which is very high, parallel this impedance ZAB, which is infinite. So these two parallel combination will be very high, because this is infinite and this is also very high. So ZCD, so therefore ZCD is very high. Okay. So for example, if this is theoretically infinite, then this is theoretically infinite. Now what will this cause? So this is the transmission line. So this is the transmission line. Okay, so this is the transmission line. And if we made Z to infinite, that means if we open circuit this, then ZCD is very high. So that means we have inserted a very high impedance in this transmission line. So this implies that so we have inserted a very high impedance in the transmission line in series in the transmission line. Firstly, we should never do it, because then if we are inserting a high impedance in series, the transmission line is disturbed, its current because we know ammeter should not have large impedance. Why? Because it should not disturb the transmission line. But here the CT is with the secondary open is inserting effectively a high impedance in the transmission line. So transmission line will be disturbed. That's one thing. So transmission line is disturbed, means high voltage drop can happen or something, but that's not so crucial. But next thing what will happen, so high voltage. So a high voltage will appear across the primary. Why? Because this is a transmission line which is carrying a high current. Okay, so a high current transmission line, now a high impedance is inserted, high current times high impedance is a high voltage. So this voltage will be very high. So primary voltage is very high, and now this CT is actually a step up transformer. So secondary voltage will be even higher. Secondary voltage will be even higher. Because CT steps up voltage. Okay, so two factors: CTs are step up transformers, and secondly, by design we have made this impedance to be very high. Therefore, this two factor is leading to a very high secondary voltage, which can cause what? Firstly, immediate insulation breakdown, the CT will damage, a lot of damaging things can happen. Now if somebody is trying to also say connect something at the secondary now, okay, then he will face a high voltage. That's risky. So this CT may damage, okay, one factor. If somebody is going to insert something, connect something to the secondary, he might get I mean extreme uh, shock, extreme fatal shock. So this is very risky. So secondary of a CT should never be open circuited. So what have we learned so far about CT? Number one, phase error, ratio error. Why they appear? Because of the no load current I0. To reduce error, we have to make no load current small, okay, and to make no load current small, we have to have high permeability material and low core loss. That means we have to make Xm and R0 very high. Then we have also learned that this CT is a step up transformer, and by design it has a high Xm R0. Therefore, if we by mistake make the secondary of the CT ever open circuited, then it is very risky. So we should never do it. These are some things we have learned. Now let's come to PT, that is potential transformer. So let's talk about errors in a PT. Okay, so the discussion will be very similar, like a mirror image to the discussion of the CT. Okay, so we will okay. So let this be now PT with turns ratio N1 by N2 equal to A. So the secondary, of course, will now have a voltmeter V, and the primary is supposed to measure a voltage. So let's draw a voltage source. And this voltage is V1. Okay. So now let's do it this way. So what will be the voltmeter reading? Voltmeter reading will be same as the voltage that appears across the voltmeter, which is V2. And this is our so this is voltmeter reading. Now what will be our estimate of the primary voltage? So our estimate of primary voltage, this will be how much? This will be AV2. Okay. So this comes from the fact that V1 by V1 by V2 is equal to N1 by N2 equal to A for an ideal transformer, and we believe that we will think that this transformer behaves like an ideal transformer. If we think so, then we will estimate V1 as AV2. Okay. So we will, so with the belief that PT is an ideal transformer. Okay, so this is measured value. So measured value is AV2. Measured value, I am writing again, is equal to AV2. But what is the true value? True value is this, V1. True value is equal to V1. Are they equal? Is V1 equal to AV2? No, because what is AV2? AV2 is actually the voltage that appears here, V2 prime, here in this circuit. Okay, so this is AV2. This is the measured value. Okay, and the true value is the voltage that appears here. Now, there can be a voltage drop from this point to this point, because some current flows here in this circuit, and that will get multiplied by R1, X1, this. So there will be some voltage drop. Okay, so we will have some voltage drop. Okay, call it VD, D for drop, from here to here, plus minus. Okay, so then we can write V1 is equal to this VD plus V2 prime. So here the answer is no. In fact, V1 is equal to, as I said, VD plus V2 prime. So this is true value is equal to voltage drop plus measured value. Now this is a phasor equation. Okay, so therefore it's possible that V2 prime, say, let me draw that V2 prime is here, and depending on this current, okay, depending on this current, we will have some voltage drop here, 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 here. No, this is not this, only here, 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 here. So depending on this current and this current, we'll have some voltage drop. So if VD, let me draw, if I don't know, maybe VD is here, then this is V1. This is true value, this is measured value. Okay, so we have errors. What are the errors? Number one, that the magnitude of V2 prime is not equal to the magnitude of V1, which implies that V1 by V2 is actually not equal to A. Okay, V1, according to this diagram, so according to this diagram, V1 is slightly greater than, maybe V1 maybe, not is, maybe slightly greater than V2 prime. So this is called the ratio error. And the angle between V1, there should be no prime, V1 and V2 prime is not equal to 0. This is called phase error. Why phase error is important? This is important for power and energy measurement. Okay. So, if we have, once again, let me draw this. We have a source and a load. We want to measure the power. So, we have a wattmeter with two coils, current coil and pressure coil. Current coil, we connect this in series, and the pressure coil, say instead of connecting directly, say we connect it via PT maybe. So, this is a PT and we connect this here. So, now if this voltage, okay, between this point, these 2 points, and this 2 voltage between these 2 points are not in same phase, then the angle between this current and this current voltage will not be same as this current and this voltage. So, power or energy measurement will be wrong, because power factor will get changed. Okay. So, this is why it is important. Then we can also do turn compensation. How? So, if nominal ratio is N1 nominal by N2 nominal, and if we find that measured value is slightly less than the actual value, true voltage, then we can use N2 actual to be slightly greater than N2 nominal. Okay. So, then the secondary voltage will increase. Okay. Now, the next important question, very important question. Can you guess? This is the last thing. Why the secondary of a PT potential transformer should never be, can you guess, open circuited? Answer? The answer will be very similar to the answer in the case of CT. So, observe that a PT steps down voltage so that means PT steps up current. It has to be. Okay. Now, second thing, second observation. So, this is point 1 and point 2. So, this is the, say this is the equivalent circuit. Then here we have the ideal one. With N1 by N2 is equal to A. And if I call this impedance Z2, okay, and here we have the voltage source V1 that we are measuring. So if we take Z2 equal to 0, then the impedance as seen between these 2 points, call it AB. So ZAB as seen from here between these 2 points, equivalent impedance. So ZAB will be equal to A square Z2 equal to 0 if Z2 equal to 0, short circuit, right? And then this impedances, call this R1, X1, R2, A square, X2. Now this impedances has to be small by design. Okay, so I think I have forgot to mention this. Okay, so for a PT we have to make this impedances small. Why? Because if this impedances are small or 0, then there will be no voltage drop here. Okay, so to eliminate voltage drop, eliminate phase error and ratio error, we have to design the PT to have this impedances very small. So let me just tell you, I forgot to tell this before. For a PT, PT should be designed in a way so that these impedances are small. So we have to use very high conductive, low resistive coil. We have to minimize leakage reactance, leakage inductance by proper design. So PT should be designed to have R1, X1, R2, X2 very small. Okay, that's the design consideration for a PT. So therefore, this R1, X1, R2, X2 are small, very small by design to minimize error, to reduce error. Right? Now, if so, you see this impedance is 0. Okay, so this impedance is 0. So this is very small. Therefore, and this is also very small. So therefore, the equivalent impedance as seen between these 2 points, call it C and D. Okay, so think of the impedance ZCD. What is ZCD? ZCD is this impedance and parallelly this impedance. Now this is 0, this is very small. So effectively there is a very small impedance path. Okay, so ZCD will be very small. So if ZCD is very small, then we are connecting a very small resistance impedance across a high voltage source. Okay, so therefore this current I1 primary current will be very high. Okay, so this will imply I1 very high, and then I2 secondary current will of course be even higher. Okay. So, I2 will be even higher. Now, all these high currents, they can immediately damage the PT. High current can flow, it can cause a huge heat, and the insulation may burn, and it can cause a danger, it can cause some very risky things. Okay. So, the secondary of a PT should never be short circuited. Why? Firstly, this is a current step up transformer. Voltage step down means current step up, and then a PT is by design has very low series impedances. So, therefore, it will draw a high current and it can cause dangerous things. So, that is the important things. Now, let me conclude this video by saying one or two words about why or how the instrument transformers CTPT is different from a power transformer. The answer is simple. A power transformer will be designed for what? Say to have high efficiency, that should be the first factor, to have high efficiency, because they deal with very high power transmission generally. So, if their efficiency is small, we will waste power. And second factor could be low cost. Okay. So, we will not use unnecessarily high quality core because you want to reduce cost. We will not use unnecessarily very thick big conductor because you want to reduce cost. But an instrument transformer, but a CT or PT is primarily designed to reduce what? Error, ratio error and phase angle and phase error. Okay. So, if for that, if we need to put thick conductor, yes, we have to give thick conductor even if the cost is going higher. If we need high quality material, core material, yes, we have to provide it, because that is the primary consideration for a CT or PT or a instrument transformer. That is how a power transformer is different from a CTPT, primarily from the design aspect. Thank you.